All right, so in the next hour or so, we're going to talk about anomalies.
We don't see the screen, sorry. Or we don't see the video.
Ah, interesting, because we see here, right? You have to share screen, huh? Do you see now?
Yes, thank you.
Yeah, good. So anomalies and supersymmetric quantum field theory, of course, this subject that can be its own course. So clearly I have to be schematic. But yeah, I want to make a few comments. But before I do this, I want to emphasize that this thing, the SUSY localization method, is not only applicable for three-dimensional theories, right? I focused on them because somehow I thought that those are the easiest thing to explain, but it can be done for two-dimensional QFTs, for four-dimensional QFTs, 5 dimensions, and so on. So it's a pretty universal tool, and the details in each case differ, and what can be computed also differs, and you have to be a bit careful, because sometimes I told you that you have to do this only the quadratic fluctuations, let's say around the North Pole and the South Pole, but let's say in 4 dimensions, what happens is that you actually have to include also instanton contributions. There's like these like instantons, let's say, that can live on this locus. So the it can get more complicated, is what I'm trying to say. But still very interesting. Okay, enough about that. So now, what do I mean by this word? Well, anomalies in quantum field theory are these things that realize the notion that a classical symmetry can be violated by quantum effects. Classical symmetry can be broken by quantum effects. This is a very general statement, applies to all kinds of symmetries. So we really have to be careful how we use that. But it's a useful thing for several reasons. This can rule out inconsistent QFTs. This is especially valid in the context of gauge theories in 4 dimensions. There is an anomaly called the Chiral Anomaly, which I'm going to discuss actually now. And then you can think that, let's say, some SU3 gauge theory with some number of quarks and antiquarks is a good idea. But then these quarks and antiquarks can lead to anomaly in the gauge symmetry, which will make the path integral inconsistent. So that's not allowed. So this really is there's a swampland fan in the background. This is really the original swampland method. You can write down classical Lagrangians that you think are good quantum things, but they're not. So you can delineate the space of QFTs in this way. Not every classical thing can become a quantum thing. Okay. Another thing that's kind of nice for anomalies is that often they're one loop exact. Or another way to say this is that they're related to topology in some deep and important way, which I don't have the time to talk about. And so this makes them easier to compute. So in a sense, if you want to make an analogy, QFT is like geometry. It's hard. You know, PDEs are hard to solve Einstein's equations. It's hard, but topology is somehow easier to compute. So, for instance, someone has worked on Calabi-Yau manifolds, we don't know a single metric on a non-trivial Calabi-Yau manifold, but we know a lot about the topology of those spaces. So that's kind of the spiritual comment here, is that these things are somehow easier to compute because they're topological, ultimately. And in some cases, they're interesting observables, meaning physical they lead to interesting observables that you can compute. Exactly. That's what I mean by compute. Okay. So here's what anomalies are. Consider a QFT with that arises out of a Lagrangian with a classical symmetry. So you have some action that is invariant under some group of transformations. G is the classical symmetry. We say that G is anomalous if the path integral is not invariant under G. That's what a quantum anomaly is. So you start with something that has a classical symmetry, and somehow the path integral is not invariant under that. So that schematically, like this, very fluffy. So now you can at least try to classify what G can be. It can be a continuous symmetry or a discrete symmetry. G can be a global symmetry or a gauge symmetry, for instance. So, of course, analyzing each of these cases is beyond the scope of this lecture, but we'll focus on continuous ones, and somehow I will focus on the global ones. This will be roughly. I'll make some, I already make a comment about the gauge ones. So if it's a gauge symmetry, it's really not a symmetry. It's a redundancy in the description of your story. And so really gauge symmetries cannot be like that, because if you really have an invariance of the Hilbert space under the gauge group, this cannot happen. And so, yeah. So you, if you have an anomaly for a symmetry that you want to gauge, that will be an inconsistent construction. So this is this comment here, comment 1. So these are, let me call these bad. These are good. Good means that if I have a global symmetry, I don't have to gauge it. So that's what global means. So I will, if the symmetry is preserved, so if I have a global conserved symmetry, I can have a number of them. So A goes from 1 to, this, you know, labels the generators of G. I'm very abstract now. Okay, so for each generator of G, I will have a conserved current. This is what the classical symmetry does. And then in the quantum theory, the right-hand side may fail to be 0. It will be some quantity schematically written down in terms of the fields and their derivatives. And A, this quantity which is very abstract, is the quantum anomaly. So it is not such a dramatic thing. You have a symmetry which you thought you have, but instead of you now having a conserved current, you have something on the right-hand side. So if you can compute this something, you will not have a conservation of a current, but you will have a relation. You'll have differential equations, if you wish, that constrain the endpoint functions of this operator. And these are the things that are computable. So this A is exactly computable, which in turn leads to explicit calculations of the endpoint functions of this current, if you wish to modify toward identities. And that's what I call good, because it allows us to compute stuff. How many of you have seen this? Okay, so not everyone. Good. So the simplest example, the canonical example of an anomaly is the ABJ, or the Cairo Anomaly. It was found in the 60s, I think, 69, by doing Feynman diagrams and being confused, because you would expect a word identity for some U1 global symmetry, but then it's violated, so what happens? And that's what happens. But I think the cleanest way to explain, at least in my head, the cleanest way is what's called the Fujikawa method. So I'll try to explain that, at least sketch that. So we take d equals 4 and take massless charged fermion under a U1 gauge field. So my action is whatever. So it's the Maxwell term plus the Dirac action. And this capital D is the covariant derivative. The Dirac operator, F mu nu is in, the Maxwell field and so on. The bar is some conjugation of the fermion. I'm not going to write details. So now, this Lagrangian, without a mass term for the fermion, importantly, is invariant under the infinitesimal transformation sorry, psi bar 1 plus I alpha gamma 5. Okay, so this is alpha is some parameter, some real number, and this is the infinitesimal transformation. So it's the non-exponentiated one. So if you put this in the Lagrangian, I claim it's invariant. This is called the Axial U1 Symmetry. It's called axial because there's some, if I didn't have a gamma 5 here, this is an ordinary U1 symmetry, right? A field, the ordinary U1s, the field is transformed like that, right? A field gets a phase, and that phase, if it's a global symmetry, that's a constant over your space-time, and yeah, these were the types of things we had with our U1R and U1 flavor symmetry. They were like that. There were some charges, some fields. There was no gamma 5. But if it's a massless fermion, you have a gamma 5. You have this option to have axial symmetry. So gamma 5 is a smart thing. It knows about left and right. So that's why it's called axial. Okay, so there's a current, the axial current, like this. So this, I claim, is conserved for this. This is the conserved current corresponding to this transformation. So if this is conserved in the quantum theory, you will have word identities of the following schematic form. So if J mu A is conserved in the QFT, you should expect word identities of the type psi, gamma mu, gamma 5, psi. And then any operator here is equal to 0. This is the QFT extension of the Noether theorem. This is called word identity. Schematically, okay? Well, we start computing these things in perturbation theory or something, and you will see that that's wrong. These identities are not right. This is how you can find this anomaly with just pedestrian tools. without using path integral or anything else. You can start doing whatever. This is almost a free theory. The only coupling is this coupling that is cubic, so there will be a cubic vertex between two fermions and one photon. That vertex will exist, and this is your only interaction, and you can start doing loops with that and check this and see that it's wrong schematically. To me, a more intellectually satisfying approach is to study the path integral. So I have a theory of quantum electrodynamics where the electron doesn't have a mass. That's the physics of this. So my job is to compute the path integral. Okay. Okay. This is the path integral. I'm integrating over all of the fields. These are independent because, well, I forgot to say that this psi is a Dirac fermion, so it's a four-component thing. So that's not an irreducible representation of the Lorentz group. I have to split it into two vial, so two components, and so these are independent excitations, if you wish, and then I have to do this path integral. So the logic over there is that if a classical symmetry is preserved in the quantum theory, this path integral has to be invariant. The action is already invariant. You can put this here and check that it's invariant. So the only way that the quantum theory may violate the symmetry is if the measure is not invariant. So this really points to what fails. So quantum anomalies can be understood, at least in this example, arise as non-invariance of the measure under the symmetry of the path integral measure. So the claim is that this measure is not invariant under that transformation. So to really understand this, I have to inform you what is the measure in the path integral. This is a notoriously murky subject. So I will not explain it. That's how education goes. So in this case, this theory is almost free. What do I mean by this? One way to really do it almost rigorously is to freeze the gauge field. So do not do the path integral over A mu. So view the theory as a massless electron in a fixed background field. So A mu is not allowed to fluctuate. You remove this term, if you wish, from the action. But you keep this A mu non-zero. So if you wish, this type of diagram is now treated in what's called the background field method. So you freeze this propagator, and then you just have a vertex. So this is a Gaussian theory now, right? Because I cannot have loops, basically. Is this clear? Okay. So this is as rigorous as we can be with the path integral. It's almost free. And basically then the measure is, one way to deal with it is to discretize your space-time and put, a lattice of harmonic oscillators, fermionic ones, Grassmann harmonic oscillators at every point, and take the product of all those things, which is infinite, and take the lattice spacing to 0. Then this is, of course, subtle to do, and so on. So I changed the problem to this problem. And then exponent. Yeah, sorry. I'm not going to do this. This is what Fujikawa did in 1984. think. Anyway, even if it's not in that year, maybe it's earlier, but 84 is a good year. Generally. There's a book written about it, right? So it must be good. Okay. Anyway, so you really have to go and study. So this is some kind of a product over lattice points of harmonic oscillators at those points and so on. So I'm not explaining that. And then you can act on these, this lattice model, if you wish, with this transformation and see how it transforms. And if you find that it doesn't, you don't have an anomaly. And if you find that it does, you do. That is the calculation I'm skipping. I think actually I have a memory of a 1984 paper by Fujikawa, but I think he did it first in 78. He has like 2 important papers on this. Anyway, it's the Fujikawa method. It's explained in many books, including Peskin and Schroeder. Okay, so this is what happens. So if you wish, if you do this transformation, the path integral changes to this. So there's this term. So now you get, so this object is the curly A there. That's the logic. Leads you to this. So this is the violation of the conservation. This is the axial current. It's minus 1 over 8 pi square f tilde mu, f tilde mu nu, f mu nu. And f tilde is basically the Hodge dual of f up to constants. Do you know what a Hodge dual of a form is? How many of you don't? Oh, okay, that's the Hodge dual of a 2 form in 4 dimensions. Okay, so I have a non-trivial right-hand side. So the statement now is that if I really treat this A mu as a background field, is that this current, the axial current, is in general not conserved in the presence of a background field. So of course, if I put A mu to 0, it's conserved, but in general it's not conserved. But it's not conserved not in a random way, in this specific way. So this object, J mu plus, so this whole object is actually conserved in some sense. It's fixed. Okay? So that's the U1 anomaly, the ABJ anomaly, or the Cairo anomaly, many names, it's this. And so now this you can probably understand why for a gauge theory that's bad, because if you do a path integral over all possible gauge configurations, you have to allow every possible f mu nu, right? You don't have to solve equations of motion. So every f mu nu should be allowed. So this will be non-zero and you'll have a problem. But if I don't integrate over A, it's just a background field that I can tune as I wish. 5 Tesla is a good number. Okay. You don't know what a Tesla is. It's not a car, right? I mean, it is a car, but that's not how. It's a human being from Eastern Europe, and then he went to the US and was crazy then, and did amazing things. And there's some other human being from South Africa who also went crazy, and that's what a Tesla is. It's also a unit that measures magnetic field, amongst other things. Okay, so the same logic can be applied for fermions in a background metric. So here I can think of this f mu nu as the curvature of the U1 connection, A mu. If I don't have a gauge field, but I have a curved metric, I can essentially repeat the same story, and because the fermions couple to the curvature of space-time through the spin connection, I get what's called a gravitational anomaly, which is now covariant, right? Because I'm in curved space. And this is I'm not even, even remotely sketching a derivation, but this is the answer. So what you learn is that in four-dimensional spacetimes that are curved, if you have a massless fermion on them, this current J mu A is not conserved in general. Because on a general curved space, this does not vanish. These are some contractions of the Riemann tensor. And I will have a non-zero answer. So this is called a gravitational anomaly. The deep fact of life is that both this object and this object, both of them, are mu nu alpha beta, are rho sigma alpha beta. Both of them are what's called topological densities. I don't have the time to explain what this means, but roughly what it means is that, well, exactly what it means is that when you integrate these over the manifold, right, that's what a density is. It's something that waits to be integrated desperately. So these wait to be integrated, and if you integrate them, you get integers. You get topological invariants of the manifold. So the first one is related to things like Chern classes, and the second one is related to things like Pontryagin classes and Pontryagin numbers. But I'm not going to go into details of that. If you don't know what characteristic classes are, you should read Eguchi, Gyuki, and Hansen, or Nakahara, or any other of the books written on the subject. So, but just to give you a flavor, you have seen, I hope, this type of topological density. So you take the Ricci scalar in 2 dimensions, and you integrate it covariantly, meaning with a square root of g, over the manifold. You divide by 2 pi, and you get magic. This should not be called g, let's call it h. H mu nu is the metric on the 2-dimensional space. Let's call it sigma. And you get an integer. I'm assuming compact, smooth things in 2 dimensions. So this G counts the number of holes. So that's a genus 2 manifold. This is whatever, the Gauss-Bonnet theorem. This is a deep fact. This is a connection between topology and differential things, differential geometry. Okay? This is an impressive fact of life, and such impressive facts of life exist in more than 2 dimensions. Yeah, and those 2 things are such densities that when integrated will give you numbers, integers. Well, you have to normalize in a proper way. So this 8 pi square does the job properly. So, integers up to 2 pi's and so on. Okay, so that's the anomaly in 4 dimensions. The same thing works in any even D. Same effect, if you wish, in any D is equal to 2n. So there's analogous expressions for non-conservation of an axial current in 2 dimensions, in 6 dimensions, so on. In terms of Feynman diagrams, so if you really don't want to compute, if you really don't want to talk about any topological densities or Fujikawa methods or path integrals, you're a simple man, you only know Feynman diagrams. So then you should go and look at this Feynman diagram. Sorry, I'm right. So you have something. So this is, if you wish, an operator J mu, J mu, J mu, and this is the psi. So you study a triangle diagram, as it's called, a loop diagram. It's a one loop diagram where fermion runs in the loop. And if you wish, these things are supposed to, I mean, if you really want to freeze the gauge field, we can say that this is a gauge field, okay? That's another way to say it. But it's the frozen gauge field. So here you don't really have a propagator. You fix this, this information at this vertex and this one and this one, and this loop you have to do, and you'll get exactly this answer. And for the gravitational one that I wrote up there, the diagram is the same triangle, but now, if you wish, the fields are the gauge field and the metric. I don't know how to draw it, but, or a energy momentum tensor. Okay, so this is another way to compute the same thing. And so this is what I meant by one loop exact. That's it. Computing this will give you that answer. The coefficient there, 1 over 38, whatever, 384 pi squared. Okay, good. So, yeah, good. So now I want to talk about another anomaly for which I will not even attempt to explain how it's derived, but it's similar ideas. And that's the conformal anomaly. So, conformal symmetry is not gauged, at least in quantum field theory. It is gauged in string theory, which is why the conformal anomaly on the worksheet has to vanish if you want a consistent string theory. But in general, it's not gauged, and so you have. So this is the classical statement, which some of you already asked me about. The energy momentum tensor has to be traceless. So the contraction of the energy momentum tensor with a conformally flat metric has to vanish. That's one consequence of the conformal symmetry. But in a, so this is the classical. If you have a quantum theory, that's not true in general. And you have these violations of the conformal symmetry. But again, they're very controlled and very specific. There are 3 terms. I call this kappa. This is how I write kappa. If you don't like it, not much I can do about it. So that's how it's written. Anyway, but the important thing is that I have these 3 numbers. And then there's some letters here, W, E, and F. So F is a background. It's like this F here, right? It's a background gauge field. So I'm allowing that I have a global symmetry, and I turn it on. And if I turn it on, I'm going to break variance. And this is what measures that, this coefficient. This W square is the square of the Weyl tensor. If you don't know what a Weyl tensor is, you learn about it, of course, but it's given by a certain contraction of Riemann and Ricci and E is the Euler density, as it's called. So this is kind of the topological density that generalizes the Gauss-Bonnet theorem to 4 dimensions. This computes the Euler number of a 4 manifold. Sorry. So some other linear combination of these curvatures. And well, in this language, I can also write down just for fun, there's the Pontryagin density, which is already what I wrote down. R mu nu alpha beta, R rho sigma alpha beta. So these two are actually topological densities. They lead to things that are called a signature of a 4 manifold and the Euler number of a 4 manifold. These are two, so I really don't have a genus. It's not so simple in 4 dimensions. In fact, as far as I know, we don't have a full classification of 4 manifolds, so it's hard, but these two are topological invariants. These two, E and P. Okay, so I have these numbers, C, A, and kappa. And for a given CFT, they will control how much in a background metric and in a background gauge field, how much the conformal invariance is broken. Okay? So I have to compute those numbers, and they will depend on the CFT. So they contain dynamical information about the quantum field theory. Okay? So there's some important facts. One important fact is that A, the quantity A, is a monotonically decreasing function along an RG flow. A is monotonically decreasing along RG flows. So in 3-dimensional quantum field theories, I didn't have these anomalies. So by the way, I'm in 4 dimensions here. Sorry, I should have said this. There's analogous expressions in every even dimension. But in odd, I don't have a conformal anomaly. This is not obvious. We have to show it, but it's a fact. So in 3 dimensions, one thing that we found, or we discussed that was monotonic along an RG flow was this F, this S3 free energy, which is somehow, well, it's hard to compute in general. In 4-dimensional quantum field theories, the monotonic thing is an anomaly coefficient, A. So in some cases, it's easier to compute. But in general, these coefficients, A, C, and kappa, are hard to compute. In interacting CFTs, interacting QFTs. And the third comment is that the number C determines the 2-point function of the energy momentum tensor. So again, there's something that is fixed by the kinematics, some tensor, P mu, P nu, and so on. And there's one coefficient that I don't know, and it's this C. Okay? So one way to, I should have done this when I talked about the U1 anomaly, but anyway, I'll do it now. In this language, one way to write down this U1 Cairo anomaly. So I wrote it down for a theory of one Dirac fermion in 4 dimensions. this equation is valid for one Dirac fermion. So I fixed the theory and I computed this with the Fujikawa method. More generally, for more interesting quantum field theories, you should, in general, worry if they have anomalies. And to parameterize that, you can write it like this. R tilde mu nu rho sigma is just this contraction. So K, these things that I call KFF and KF, these are called cubic and linear anomalies. Okay? And they depend on the theory at hand. So for instance, if I have one Dirac fermion, Kf is equal to -1 in this language. If I have two, it will be equal to -2. But if you have some kind of more complicated example of quantum field theory, these things are in general hard to compute. Again, you might be able to compute them, you might not be able to compute them, but you parameterize it in this way. So these things, when you have a global symmetry, these things are called Tuft anomalies. And they're called like that because Tuft, among the zillions of important things that he did, he emphasized the fact these things do not change along RG flows. So if you start from some Lagrangian in an asymptotically free theory, and then these are somehow easy to compute because I have an explicit action, and these are related to the charges of the fermions in that action. If you compute them in the UV and you undergo an RG flow, they will be the same in the IR. I don't have time to explain this argument, but these are invariant under RG flows. So you compute these things by essentially for every field, so KFFF is a sum over massless fermions. And for each of them, you compute, roughly speaking, their charge cubed. That's what this is. This triangle diagram I was erasing boils down to that. This is why this is easy to compute. If you know the charges, it's a simple equation. And this is even simpler. It's just, again, sum of the charges themselves over fermions. Okay? So if you have a Lagrangian in the UV, you just analyze what are the global symmetries. And for every field, you write down the charge. You look at the fermions, chiral fermions, and you assign, look what their charges are, and you put them in this formula, and you're done. Okay, so these are easy to compute. These are hard to compute, A and C and kappa. Now, you can probably see where this is going. When you have a supersymmetry, magic happens. Hard things become easy things, and easy things remain easy. That's what happens. So again, the logic is the same. When I have a supersymmetric theory in 4 dimensions, so the minimal amount of supersymmetry is 4d n equals 1. This thing automatically has a U1R symmetry. The multiplet of the energy momentum tensor contains this U1R current, 2 supercurrents, as they're called, fermionic gadgets of spin 3/2, and the energy momentum tensor. So this J mu R will have such a triangle anomaly, which I can compute by elementary means if I know the R charges of the fields. Then this will lead to, well, this will be the anomaly. This is what I put here in these equations. But supersymmetry will relate that to the anomaly of the energy momentum tensor, which is up there on the board. So the coefficients, what I call KRRR, because it's R symmetry, are related to the coefficients C, A, and kappa. This is due to a supersymmetric word identity, or a bunch of them. This is due to supersymmetry. So essentially what you have to do is you have to begin with this equation, put R here, and start acting with Q's in a clever way, because acting with Q's on J will build me the energy momentum tensor. And so then I act with Q's here, and those Q's will have to act on these fields also, on these background fields. We know how that works, and then you will find how this converts into that, but the coefficients have to stay the same because they're real numbers, not fields, and you find relations. This is not easy to do. You have to really sit down and work. But of course, here we don't work. We just write answers. So here's the answer. Kappa is minus C over 6 pi squared. So in a 4-dimensional n equals to 1 superconformal field theory, instead of having 5 independent anomaly coefficients, I have only 2. You can call them any way you want, either these two, or A and C, or something. So I went from 5 to 2. Okay, so at this point, you should be happy, because I told you that these K's are easy to compute. They're just sums over charges. In turn, computing them automatically fixes A and C, which are the things that are hard to compute. So for an interacting QFT, A and C are hard to compute, and K are not hard. So we just won. Yes? Yeah, this is an non-perturbative statement I make. No meaning. No meaning. There's no diagram here, it's just an equation. Of course, you should be, yes. The real question is, why is this thing one loop exact? That's a rephrasing of your question, and that's a deep fact. That has to do with the fact that these are actually topological densities, so they cannot be changed by anything. So that's the deep fact. But otherwise, I just gave you an algorithm to compute if you have an asymptotically free theory. Yeah. Sorry, which anomaly? K and A and C. Oh yeah. So this is a superconformal fact. Yes, this is due to supersymmetry. Otherwise, this equation up there, C, A, and kappa, and this equation here, KFFF and KF, these are non-supersymmetric facts.
Yeah, but I'm a bit confused by the fact that why the first equation relates the R current, the anomaly the R current with the conformal anomaly, the last one, the relation between two conformal anomalies.
If you wish, I have here two, well, roughly speaking, I have here two terms, and there I have three, so I find the dependence because of this word identity. It's yet another word identity. Yeah, as I said, it's not obvious, but it's true. Right, indeed. If I don't have supersymmetry, this is an independent number. And sometimes you don't see it because it's somehow, kappa exists only if you have U1 or whatever, some global symmetry. So many people just write the first two terms and say that's a conformal anomaly, which is a true fact in general. But if you have flavor symmetry, you have to add an extra term. And that term is an independent, has an independent coefficient. Okay, so that's the general story. So let's try to use it to compute stuff. So the harmonic oscillator of the 21st century is n equals 4 Young-Mills. This is what famous people in Princeton claim. It might be a wrong statement, but it's still a good, interesting example of an interacting quantum field theory. So let's study that. Okay, so I have an n equals 4 super Young-Mills theory. I can think of it as an n equals to 1 theory, because it certainly has n equals 1 supersymmetry. It has much more, but when you view it, view as n equals 1 theory. And then this theory has one vector multiplet. And again, I'm only writing down shell degrees of freedom, meaning I'm ignoring the auxiliary fields. So there's 3 chiral multiplets, phi. And for each of them, I have a scalar phi I, a complex scalar, and a fermion. So this lambda is called the gaugino. It's a spin 1/2 field, and this is the gauge field. And all of these fields are in the adjoint of the gauge group. Okay? So I told you what the field content of the theory is. I haven't told you what the Lagrangian is. I'm not going to do that, but I will write the superpotential. So the superpotential is very specific, fixed by the big symmetry in the problem. So that's the superpotential, and the trace is over the adjoint of the gauge group, because every field is a matrix, right? Okay, so this theory has, well, has SO6 global symmetry, which is an R symmetry. SO6 is isomorphic to SU4 as an algebra, and that SU4 rotates the 4 supercharges. However, here in this n equals 1 language, what's manifest is SU3 times U1. So from the point of view of the n equals 1 algebra, this SU3 is a flavor symmetry, and this U1 is an R symmetry. This one is the supraconformal R symmetry that I have to use in this identity. So now you have to find the charges of every field under that U1 R symmetry. The superpotential has to have R charge 2, which by now you've heard many times from me. And so that immediately fixes the R charges to the chiral multiplets phi I. So phi I has R charge equals to 2/3. This is the R charge of the chiral superfield, the multiplet, and it's equal to the R charge of the lowest component, which is a scalar field. However, if you recall, these chi's are fermions, and when you expand the superfield in components, there's some thetas multiplying the fermions, so they eat up R charge. And so chi always has one R charge smaller than phi. This is fixed, so if you fix the R charge of this, you'll know the R charge of that. Okay? So the charges of the 3 fermions, because my rule was that I have to do it for the fermions, is that. I haven't talked too much about this multiplet, but the way to fix the R charge is to know that the gauge field is invariant under the R symmetry. Okay? This lambda, so for this to have R charge 0, this has to have R charge 1. It's not obvious because I haven't talked too much about these multiplets, but it's simple to derive. So the R charge of lambda is equal to 1. And so I have the charges of the fermions, and I have to do this sum. Now I have to remember that each fermion is has a fermion index. It's a spin 1/2 fermion, but it also is an n by n matrix, if you wish. So it's in the adjoint of the gauge group. So if the gauge group is SUN, right, this will be n by n matrices. And so K R R R is equal to this guy. I have how many of them? Well, the dimension of the gauge group, dg. And each of them has charge 1 to the power 3, just to make this formula manifest, plus 3 times the dimension of the gauge group times minus 1/3 to the power 3. So I have 3 chiral fermions. Each of them is a n by n matrix, if you wish, in the adjoint of the gauge group. That's where this factor comes from. And each of them has charge minus 1/3, and I have to raise this to power 3. This is some simple algebra to do here, and you find this. Kr is the same logic, dg times 1 plus 3 times dg times minus 1/3. This is the linear anomaly, so everything is to the power 1, and you get 0. Okay, so you'll learn a few things. Well, you'll learn explicit expression, so just to be very explicit, for SUN, the dimension of the gauge group is n squared minus 1. You also learn that n equals 4 Yang-Mills does not have a gravitational anomaly. So n equals 4, if you put it on any amount for the metric, this current will be conserved, the one that we talked about. All right. Good. Now I've computed this literally in front of your eyes, and so then I can use those word identities here, these things in the box, to compute the conformal anomaly of n equals 4 Yang-Mills. And that is, you find the exact relation that A and C for n equals 4 Yang-Mills are equal to each other and are equal to 1/4 times the dimension of the gauge group. And this is a non-perturbative statement. True fact. Okay. So life seems good, right? So for instance, this immediately computes for you the 2-point function of the energy momentum tensor in this quantum field theory. It's proportional to C. At this point, you can say, okay, this is so much easier than this localization stuff, right? There I had to go through the motions and compute this f of S3 and differentiate it, score spheres. It seems like a nightmare. Here, some charges, some elementary algebra. There's still something you should worry about here, and it's exactly the same thing that you should worry in 3 dimensions about. How do you fix the R charges? How did I know? In this example, everything was fixed because, well, there's a symmetry in the problem here, permutation symmetry. So every single one of them has to have the same R charge. And that fixes them to be 2/3, because the total thing has to have R charge 2, and they have to be equal, and that's 2/3. But in some cases, well, in most cases, this niceness will not happen. And so you need some method to fix these R charges. And there's a beautiful way to do that. It's called A maximization. So now this demystifies a little bit why Jafferis was looking to maximize something. He knew about A maximization. And the reason he knew about it is that he read the archive. So it appeared before he was talking about F maximization. So I will briefly explain what you have to do. So A maximization. So in a four-dimensional n equals to 2 superconformal field theory, the following fact is true. You can assign arbitrary R charges to all your fields with the constraint that their sum has to be 2. You know, if you have a potential, that has to have R charge 2. That's the only constraint. And otherwise, you assign random values. Let me call them Si. And so this we will call the trial A. So you'll make a guess. This thing now is easy to compute because everything is just algebra. I assign to every field arbitrary charge, and I have to do this kind of, you know, charge to the power 3, sum them up, and that's my answer. So I'll have a function of Si. And then, to fix the Si, you have to solve two equations. Well, one equation, really. You have to solve this algebraic equation, and you have to pick the root that that gives you the maximum. Okay? So this was proven by Intriligator and Wecht, and you can really prove this. And the only assumption, so this comes from a word identity. This is an identity is equal to 0, can be completely derived by using supersymmetric word identities. No mystery here. This assumes unitarity. So the sign here is because this is proportional to minus something that has to be positive because of unitarity. So unitarity, by the way, fixes A and C to be positive. And that's what you use here. Okay? So now I have a tool. And it's the logic is exactly the same as in F maximization. You start from some asymptotically free theory. You assign charges. You compute the quantity that needs to be extremized. In this case, it's a very simple thing to compute. You don't need to know about dilogarithms and localization and fancy stuff. You just need to know about cubic and linear anomalies. You compute that. Solve these algebraic equations and pick the root that gives you negative Hessian. Okay? Is that clear? What the logic is. Okay, so I'll do this once so that you see it at least once in your life, how it works. I was struggling to find an example that will allow me to be pedagogical. Anyway, I will give you an example where I would spare some details because we really haven't talked about Lagrangians for four-dimensional Yang-Mills theories. So yeah, I'll just sweep some details under the rug, but otherwise I'll try to show you how it works. So the example is four-dimensional n equals 1 super, what? People call it super QCD, but let's not use those words. So you have some U1 and C gauge theory plus 2 times NF Cairos in the fundamental. So these fields, you can think of them as glorified quarks. They're in the fundamental of the gauge group. And then you add 2 other Cairo superfields, phi 1 and phi 2, in the adjoint. Okay? And you don't write a superpotential. So at this point, you may say, oh, wait a second, if I don't have a superpotential, I don't have interactions, but that's wrong because I have a gauge field now. And so these things are going to couple to the gauge fields. They are in the fundamental or in the adjoint representation, and that will induce interactions. So this is a non-trivial quantum field theory. This number is 2 because, well, you have some constraints. So NF has to be less than NC, I think, or maybe 2 NC. I think it's, yeah, I think it's less than NC, and this number has to be 2 because if you keep this NF and you increase this number, the beta function is going to turn positive and you'll lose asymptotic freedom. So I insist that this is an asymptotically free theory. So at very high energies, it's a free theory. I have a Lagrangian. I can write it down. And then at low energies, the beta function is going to make the gauge coupling grow, and I'll have some strongly coupled interactions. And then the claim is that this will be a CFT. Yet again, I'm emphasizing that this is a claim that we don't have a proof of. We can only provide circumstantial evidence for that. So now I will assume that this thing will hit a CFT in the IR, and we'll try to compute the conformal anomalies of that CFT. That's the exercise. So the R charges, so these guys will be called QI and QI tilde because Q sounds like a quark. It's not a supercharge. So maybe small q, I don't know. So these are the quarks in this super symmetric quantum chromodynamics. Their charges have to be equal. So this is the thing I'm hiding. So to really study this, I have to write down or explain to you how to write down SUSY Lagrangians with gauge fields, and then you could really see how it works. So R phi 1 is Z, and then this guy is fixed by the Lagrangian. So I have two free parameters, Y and Z, and then the third guy has a fixed R charge in terms of those two. And X will be the parameter that controls this. So I still have some freedom here to choose the gauge group and the flavor group, or the number of fundamental fields, and this is this X. So I have two parameters that I don't know, Y and Z, and I have to find them. These quantities are again the R charges of the scalar fields in those multiplets. These are Chiral multiplets. So to get the charges of the fermions, I have to again subtract 1. So these are all of my fields. So now this is a simple algebraic exercise. So K R, maybe I should erase here to have more space. So I have to compute this quantity A as a function of Y and Z, and then extremize it, maximize it. So K, R, 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 I'll be very explicit. Sorry, and I have one more, which is the gauge multiplet. So the R charge of the fermion in the gauge multiplet is, again, 1 by the same token. This is the gaugino. It's the friend of the Yang-Mills field, and it always has R charge 1 in a Lagrangian theory. Okay, so now I take how many of these I have. Well, this is again in the adjoint of the gauge group, so I have NC squared of them. I'm using UNC as a gauge group. 1 to the power 3, NC squared, Z minus 1 to the power 3. Where does this come from? This comes from this guy. Phi 1 is in the adjoint. So I have NC squared such fields. And each of the scalars has R charge Z, but then the fermion has Z minus 1, and that's cubed. I keep on going. I have another adjoint phi 2. And then this is the R charge of the scalar. Minus 1, I should erase this. So I get minus z plus 1 minus y over x cubed. And then finally, I have the fundamental fields. So the fundamental fields have two indices. Each quark has an index that goes from 1 to nf. That's this I index. I have nf quarks. And each of those quarks is in the fundamental of the gauge group. So I have a vector of length nc. And I have two such things. So I get 2 times nf times nc. So this is the number. And then the charge is y minus 1 again, cubed. So this is how easy it is to compute this cubic anomaly. Exactly the same logic gives you, I will not explain every term, but essentially for everything here, I have to put to the power 1 all of these charges. Z plus 1 minus y over x plus 2 and c and f y minus 1. Okay. So I've computed now these two terms, these two anomalies, and then I use the word identity that the A anomaly is related to these two things by a linear relation. This comes out of here. You can multiply the first term by some constant, add it to the second term, cancel the c, and you find this relation. And so I have to shove these things in this equation, get a big cubic function of y and z, right? So this, I'm treating this as a function of the unknowns in the problem, y and z. It's literally putting these two here. I'm not going to write it down, okay? And I have a cubic function to extremize. So I take one derivative, and this leads to quadratic equations. So I always, to find the R charges, I always have to solve quadratic equations, which is kind of interesting numerology, is that the R charges of 4D n equals 1 CFTs that arise from this procedure are always algebraic numbers. You're not going to find zeta of 3 or log of 2 as an R charge, because those cannot be a solution of an algebraic equation. As far as I know, it's no one understands why this numerology is true. There's no fundamental principle I know in physics that forbids to have a 4-dimensional n equals 1 CFT where the R charge or the dimension of a chiral operator is equal to zeta of 3. No principle of science forbids that, but it seems to be true. So it's kind of, yeah, homework. Understand why that's true. Anyway, so we differentiate this with respect to y, put that expression to 0. We differentiate this with respect to z, put that expression to 0. So you have to solve two equations. So a system of two quadratic equations for two variables. This is something that you learned in 6th grade or something. 2x 26x minus 1. So this is the solution. It's not very illuminating, but my point is that this can be computed explicitly. 2 times, sorry, there's no x, it's just 2. Okay, these are y and z. And these are the extremal values, so let me call them star. These are the things that extremize this. Actually, there's other roots. So it's a quadratic equation. I have multiple roots. But these are the roots that will lead to a maximum of the function. And then you have A, lo and behold, I'll write it out again. It's not very illuminating. The point is that it can be computed. And again, this is a non-perturbative answer. There's no small parameter in this equation. 9, 1 minus 8x square. So x was this ratio of NF of NC over NF, which you have to fix. And you have to obey some identity that x is smaller than 1 or 2. I forgot to write it down, but x is smaller than that. And yeah, so that's your answer for the A anomaly. You can also compute the C anomaly by taking the other linear combination up there. I'm not going to write down this expression. So with this method, you can compute the anomalies of strongly coupled quantum field theories. And it has been applied to numerous examples of varying degree of complexity. It's a very useful method. And as you see, I could do the calculation almost in real time. It's not so hard. Any questions about this? All right. No questions. So we move on. The final thing I want to mention will be really brief. So far we found some kind of extremization principles, or discussed them at least, in 3-dimensional n equals to 2 CFTs, in 4-dimensional n equals to 1 CFTs. So you can wonder, when does this happen? So the reason this happens, one way to understand this, is in terms of mixing of a U1R symmetry with a U1 flavor symmetry. So as I told you, well, in this model also, I didn't write it down, but the UV Lagrangian has a U1 flavor symmetry. And so that is what can happen. In the UV, I can have an R charge and a U1R symmetry and a U1 flavor symmetry, but in the infrared, I have to have a superconformal U1R symmetry, which will be some linear combination of the two. So roughly speaking, every time that you have a U1, when you have a SUSY algebra, superconformal algebra with a U1R symmetry, you should be asking now, do I have an extremization of some sort? And then you go through the list of superconformal algebras and you learn that the 5-dimensional one, there's only one superconformal algebra in 5 dimensions. It has SU2 R symmetry. And so that thing is fixed. The R charges are fixed if you have a Lagrangian, and that's it. In 6D, you have 2 superconformal algebra. One is this 1, 0 algebra, and the other one is 2, 0, the mysterious one. One has SU2R symmetry, the other one has SO5R symmetry. So again, nothing in 6. So you have to go down. In 4 dimensions, I told you the story. In 3 dimensions, I told you the story. So the final, if you wish, piece of the story will be in 2 dimensions. So we haven't really talked about the algebras in 2 dimensions. But in 2D, there's an obvious notion of left and right chirality. Z and Z bar, if you wish, in complex analysis. And so the supercharges in 2D are labeled in this way. As I told you, that also happens in 6 dimensions. And so the 0, 2 or 2, 0 algebra is the smallest algebra that has a U1R symmetry. So this is, it's not the minimal amount of supersymmetry. I can have 1, 0, 1 is the minimal amount. This is close to minimal, and it has a U1R symmetry. And this U1R is on the right-hand side here. So if you wish, if you think of a 2D CFT as a holomorphic and anti-holomorphic sectors, you know, Z and Z bars, the anti-holomorphic is non-supersymmetric, and the holomorphic is actually supersymmetric. So that's the setup. And the story is very, very similar to 4 dimensions. In fact, it's easier in some sense. The 2-dimensional conformal anomalies, so without supersymmetry, you have this. C is the sum of the 2 central charges of the Virasoro algebra. You've heard about the Virasoro from Monica, right? Yes? No? Yes. Okay. So these, I have left Virasoro, right Virasoro. These are the 2 central extension. This other thing that control the central extension. And C is the sum. R is the Ricci scalar of the 2D manifold. And then if you have a current, J, it has an anomaly, but it's what's called a quadratic anomaly. It's a diagram of this type. Instead of a triangle diagram, it's a bubble diagram that controls this coefficient. And you have one more anomaly, which is kind of a funny one. This also happens only in 2 and in 6 dimensions, and also in 10 dimensions. So when you hear about anomaly cancellation of string theory, it's this kind of anomaly that people got excited, and that happened in 1984. So that's an important year. Right. So there's this non-conservation of, so this is not very covariant expression. There's a reason for that. I don't want to go into it. But this is a pure gravitational anomaly, this K. And these things exist in 2, 6, and 10 dimensions. Okay? So if you, for instance, if you study a theory of quantum gravity, so if you want to integrate over metrics in 2 dimensions, 6 dimensions, and 10 dimensions, you should cancel this anomaly. This should vanish. Yes. Yes, yes, yes. I'm not sure if, yeah, the anomalies don't, yeah, so Majorana-Weyl contributes to this anomaly. That's a correct statement. But also in 60, other things contribute. So this self-dual 3 form that I told you about contributes. In 10 dimensions, you can have a self-dual 5 form that also contributes. So yes, it's related, but not, I'd say, yeah. There's other things that contribute to this. So, for instance, in 2 dimensions, there are these exotic objects called, man, how are they called? Chiral Bosons. Chiral Bosons. So one form in 2 dimensions can be self-dual. So a derivative of a scalar, you can impose a funny condition, which is d phi is equal to star d phi. This is a 2-dimensional equation. So this gadget now doesn't actually admit a Lagrangian. So this notion of chiral fields that are bosons exists in 2, 6, and 10 dimensions. And those also contribute. In addition to Majorana-Weyl, these things in 2 dimensions also contribute. Okay, let's not go there. So now, so this is these are the non-supersymmetric anomalies, and when you have supersymmetry, there is word identities. And here also we have supersymmetric word identities. And yeah, I see. Maybe there is another term. Yeah, indeed, this. Yeah, maybe. Maybe I did the mortal sin of forgetting something in the first line there. That's what. Ah, here. Yes. Yeah. Sorry. Yes. Yeah, this has to do. Let me not go. There's a reason this is non-covariant, and the reason is that I have chosen to cancel that anomaly, the one that you're talking about. So you can kind of shift where the anomaly lives. We can go into more details. It's actually explained in Peskin-Shorter, precisely this fact. That's where I learned it from. Yes. You can write the thing in a covariant way and have two terms, but actually only one is the physical one, yes. It's like in 4 dimension, there's a box of the Ricci, right? Like in the, you can put an extra term in the conformal anomaly in 4 dimensions that has some derivatives of the Ricci scalar, I think. And that looks like an anomaly coefficient that's independent, but it can be killed with counter terms. So it's something like that here. Yes, sorry. Anyway, I want to finish, so I'm taking too much time. So the claim here is that when you have n equals to 0,2 SUSY, you have, so that's a non-controversial claim. It's just true by the algebra. So the 2-point function of the arc current is controlled by this anomaly, and it's related to the 2-point function of the energy momentum tensor. So there's many notion of R here. I should be, apologies for that. One should be a bit careful. So there's left and right, and there's also R for the R symmetry. Sorry, one thing that I didn't tell you about, sorry, I'm not very, I didn't tell you about this because I didn't write it. No, I did. This is a non-supersymmetric statement. That this K is actually the difference between the two central charges. This is a supersymmetric statement. So now, if you have a supraconformal field theory with this amount of SUSY, and if you compute K and K are R, you compute the conformal anomalies. And again, because you, yes?
In 2D CFTs, you normally match up the left and right sectors by considering modular properties of it. So if you wanted the same kind of modular invariance, you still just have SUSY on one half of it, or do you then need SUSY on both sides?
Yes, very good question, indeed. If you're, this will open up one of my rants, such is life. So the rant is as follows. In condensed matter physics, you should not give, you should not care about the modular invariance. So for instance, if you want to study some edge modes that are two-dimensional, you can perfectly have Cairo CFTs that are, let's say, empty on the left and have something non-trivial on the right. This happens all the time. The modular stuff comes from you wanting to do fancy things. You want to couple the CFT to gravity, and you want to couple it to any manifold. And in particular, you want to be able to put it on the torus. And you want to have a partition function that's invariant under the, whatever it's called, the fundamental group of the complex structure deformations of the torus. That's the modular group. What acts on tau. So that is this doesn't really come from the physics of a CFT. This comes from you wanting to do imposing extra constraints on the physics. But if you want to do that, then indeed this is a very, very deep symmetry, modular invariance or modular covariance that constrains a partition function and in a sense mixes the left and right sectors. And if you have this thing K non-vanishing, you in general break modular invariance. So there's some, if K is an integer, so if K is a multiple of 24, 24 is some natural number. So it's actually allowed for k to be non-zero and still have a modular invariance if it obeys this. This appears in string theory. Anyway, you're asking about, can I have modular invariance with 0,2 supersymmetry? The answer is yes. And it's important because otherwise the heterotic string will have a problem. Yes. Yeah. So the fastest way to answer is using the heterotic string. It's anomaly free. That's a famous fact. So yeah. But yes, there's more simpler examples than that. Yes. Because in essence, if you wish, I can have a left-moving sector that is non-supersymmetric but has the same central charge as the right-moving sector. This will be 0, and I'll have modular invariance. So this is what will introduce a modular anomaly, if you wish. Yes. What am I trying? Yeah. So now the same question arises as before. What if I have a UV description of the theory in which I have a U1R symmetry and a U1 flavor symmetry? They can mix under an RG flow. How do I solve this? You solve it in the same way. You assign R charges. You compute a trial central charge as a function of the R charges. This is now a quadratic function, and you extremize it. You solve this equation, and that fixes the R charges. This is called C extremization. So that's really, I'm not going to give you examples. So, final comments. In 2 dimensions, there is, so in 4 dimensions, we have an A theorem. So the A conformal anomaly decreases along RG flows. In 3 dimensions, we have an F theorem. F, the free energy on S3 decreases along RG flows. In 2 dimensions is actually the simplest example and the first one identified. So in 1986, Zamolodchikov, Z, okay. So he wrote a paper that is literally 1.5 pages, so you should read it. It's really simple and beautiful, and he proved that C, this C, the unique conformal anomaly in 2 dimensions, is monotonic along RG, monotonically decreasing along RG flows. So this is actually the first example that realized this intuition. And it started off this idea to try to look for such functions that are constant at fixed points of the RG, and then evolve between them and somehow increase. That's one comment. Another comment is that these principles of A maximization, F maximization, C extremization they are useful, but sometimes they can fail, because what can happen, so you have some UV theory, and let's say it has a U1R symmetry and a U1 flavor symmetry. It undergoes an RG flow, and it arrives at some IR CFT. But, as we discussed on Wednesday, symmetries can emerge in the deep infrared. This is a general statement. You can start with something that doesn't have a Lorentz invariance, like a lattice, and get Lorentz invariance emerge, or conformal symmetry emerge, or what else did we talk about? Supersymmetry emerge. So a much more mild thing to emerge is a U1 flavor symmetry. So the IR CFT will have some correct supraconformal R symmetry, which is the thing I have to find using the principles of maximization, and then some strange, let me call it U1 tilde of little f. So this guy exists nowhere else along this RG flow, except at the fixed point. It emerges there. It's an accidental symmetry, as it's called. So if you have such a situation, the application of the method may fail, and generically fails if you're not careful, because you start assigning, so if you wish, there's some mixing, because you see, this R tilde, I think, because I only understand the UV. The IR is what I want to answer, but I'm too weak to answer it in general, so I'm trying to find tools. And from my UV understanding, I have a conjecture. I have one number to find, alpha. So I have to extremize a function of one variable, if you wish. But actually, it's a function of two variables, which I didn't know because I only know the physics here. I only know the Feynman diagrams and things like this. I live here, and I want to extrapolate to this point. And it is a fact of life that a function of one variable may have a maximum, but that may not be a maximum of a function of two variables. If you like skiing, which I don't ski well, but if you do, and if you are adventurous, you can experience this fact that you can have a maximum here, but you know, you can go downhill. So this can lead to accidents, not skiing accidents, but RG flow accidents. And so you should be aware that such things may happen, and they do happen on sufficiently exotic examples. And the final thing I want to say is about two-dimensional CFTs. Or in general, when we talk about CFTs, we kind of assume that there is a conformal vacuum. That's kind of all these endpoint functions I was writing down. They really mean I choose a conformal vacuum and I compute an endpoint function in a CFT. Good, so that's one assumption, that you have this vacuum. But another assumption is that this vacuum is what's called a normalizable vacuum. If you wish, you want to have things fall off sufficiently fast, just like when you compute a wave function in quantum mechanics, you want it to be L-square integrable, right? Because you want to be able to compute a probability, which is an integral of the square of the wave function. So such a condition is very implicit in you know, CFT discussion, but it can actually come and bite you. So as far as I know, in 3 dimensions and in 4 dimensions, well, at least I don't know examples of a theory that is a CFT, but I have a normalizable vacuum. So then you have problems when you compute probabilities and correlation functions. In 2 dimensions, it's very easy to find examples. The reason is that in 2 dimensions, the solution of the Laplace equation is a logarithm. Okay? Right. So in 4 dimensions, you have the Newton law, 1 over r, which leads to 1 over r squared. In 3 dimensions, you get 1 over r. In 2 dimensions, you get a log. This log is, well, diverges at infinity. It doesn't fall off. And so if you now want to make a quantum theory of this field, of this scalar field, you'll have a problem. Because the 2-point function of the scalar will be not, so I told you that in CFTs, operators should have polynomial decay with some power, right? But in 2 dimensions, if you solve this for a free scalar field, you will not find this, you will find log. So I should say it like this. And so this is not a CFT. The reason is that this vacuum is not normalizable. So this is what I had to say. So these things are called non-compact bosons or scalars because they live on a target space which is the real line. This field takes a value on the real line. Of course, I can have multiple such scalars, and they will live on some flat space of some dimension. So if you have such things in your life, you really have to worry about applying this C extremization tool, but you also have to worry, even without supersymmetry, how you compute stuff. One way to resolve the problem is to study a compact boson, which is that you identify phi plus some constant, let's not call it C, whatever, eta. And so this eta is some periodicity in field space. I'm still on R2 in my QFT, but the field space I have imposed on periodicity, so I think of this as a coordinate on S1 in field space, and then this log is gone. But then I have to study what's called vertex operators with some 2 pi's or something. So then phi itself is not a good operator because it's not invariant, but this is a good operator. And so this is one way to evade the problem in 2 dimensions. Okay, I think that's all I wanted to say. So at this point, I really stop. Thanks so much. Yeah. Questions online, offline? Yes.
Well, what about the level theory? I mean, technically, it's spontaneously broken as it looks.
Indeed. Yeah. So, indeed, you have to worry also about such spontaneous breaking of the symmetry. Yeah. So as I said, you cannot really prove that you have a CFT. You kind of have to assume a bunch of stuff, compute, and see if things are consistent with unitarity and other expectations. So yeah. Of course, many things can happen along Archie flows. Yeah. If it's spontaneously broken, something should break it, and that's usually a vacuum expectation value of something. So it's a one-point function. One-point functions are incompatible with the conformal symmetry. So that argument kind of connects the conformal symmetry assumption with the spontaneously broken. Yeah. Yes, other questions? Okay, everyone is tired. People online? No? All right, good. Thanks a lot. Let's go have lunch.
So on behalf of the organizers, this is the last lecture of Nikolay. I would like to thank him on behalf of the organizer, of course, I would like to thank him for the impressive set of lecture. Thank you so much, Nikolay. And